Welcome to the BAA's Autumn Webinar. As usual, we're running the webinar using Zoom with a live stream to YouTube, and the recording will be available to watch on our YouTube channel shortly after the end. You can ask questions by typing them in the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end. It's my pleasure to hand over to Alan Lorraine, the President of the BAA.
Thank you very much indeed, Andy, and good morning to those watching on Zoom, and hello to those watching on catch-up on the BAA YouTube channel. So this morning, as in normal circumstances, I would have said welcome to Leeds, obviously with continuing difficulties on the pandemic that we've replaced the autumn meeting with a webinar again. And so today we've got Dr. Manisha Reshaya, originally from Kathmandu in Nepal. She received her PhD over in Denver in the States, but is now working in Liverpool as a postdoctoral fellow at the Astrophysics Research Institute in Liverpool. Her research focuses on gamma ray bursts, kilonova, instruments characterization, and the interstellar medium and circumstellar material around massive stars. So the talk today, Stellar Wind Bow Shock, Laboratory to Studies Stellar Wind and the Interstellar Medium. I'd like to pass you over to Manisha. Thank you very much indeed.
So I will first share the screen. Okay, you can see the screen, right?
Yep, can see the presentation, thanks.
Okay, great. Yeah, thank you very much. And thank you to Andy and Lauren for having me here, and all the organizers for organizing this this talk. It's such a great pleasure to be here and talking to you all. And also thank you to everyone who is attending this on Saturday morning. I hope it will be something interesting to you all and also something fun. So, so currently, like in introduction, I am mostly working on gamma ray bursts now, but this is most of my work from my graduate study for my PhD. So I will be talking about stellar wind bow shocks, a laboratory to study stellar wind and interstellar medium. And as we go along, I hope it will make sense what I'm trying to talk about in this title. So let's get started. So I would like always, whenever I give talk, I usually start with this very simple figure, which I'm pretty sure most of you already know it, but it's a way for me to take a step back and to see what is the bigger picture or what we are trying to understand here. So you have this simple diagram of stellar evolution. So you have a star forming region where you have formation of star happening. Once the star formation happens, it can evolve in two different directions, depending on the mass of the star. So if the star is very massive, or more than 8 solar mass, then it evolves in this direction. And if it is lower than 8 solar mass, then it evolves in this direction. So here, example, the sun, when it is in main sequence phase, that is where you have hydrogen-hydrogen fusion happening at the center. It is creating energy outwards, and you have this gravitational pull coming inwards, and these two things balances out, and basically you get this stable, in a sense, a stellar source. Now, these evolution last for billions of years. So once it runs out of hydrogen, then it goes to another phase, red giant phase, where you have helium fusion happening. After that, once it runs out of helium, now not any more higher fusion can happen, and it ends its life as this beautiful pictures you see of like different planetary nebulae, where it leaves all this stuff away, and then you have this white dwarf at the center. However, if it is more than 8 solar mass, then the evolution is slightly different. The main sequence phase is again the same. you have hydrogen burning phase happening. That is the energy that is sustaining and making it a stable source. However, for high massive stars, usually it can keep fusing higher and higher elements because the gravitational force is high enough that you can fuse these higher elements. And this fusion keep happening until we go to the iron burning phase, where the iron fusion actually requires energy rather than producing energy. So in that case, you can imagine there is an imbalance in this nice balance that we were seeing before. And because of that imbalance, you have these supernova, these very, very explosive events where you spread out all the stuff that was formed in these stars. And I'm pretty sure a lot of you have heard these, we are made of star stuff. And a lot of times it is the higher elements that formed in these massive stars that get thrown away throughout the galaxy. And that's how we basically are here. And then at the end, we are left with a neutron star or a black hole, depending on how massive this star was during its explosion phase. Now, for us as a group, when I was doing my PhD, we were very interested in understanding this relationship between massive stars and supernova. Now, here is a very simple picture, right? You have this massive star turning into supernova. But the problem is these evolutions are happening in millions of years. There are a lot of different kinds of massive stars, and there are a lot of different kinds of supernova. And we don't have this nice map which kind of massive star turns into which kind of supernova. So we are trying to figure out how these relationships are, and for different supernova, what is its progenitor. So that was the bigger picture or motivation for us as a group to study these objects. And some of us were working on the massive star side of the things. Some of us were working on supernova side of the things and trying to bring it together. And what I was working on was on massive star side of the things. So massive star produces a lot of this stellar wind, and especially when they are towards later stages of their life, and it loses mass via radiation pressure, and the speed of these stellar wind can range from 20 to 2000 kilometers per second, and the mass loss rate is pretty high, like it can be up to 10 to the negative 6 solar mass per year. So these massive stars are losing mass in these local their environment. And then you have interstellar medium. So interstellar medium basically is any space between two stars, right? But it is not empty. It has gas and dust, and the properties of these gas and dust varies at different part of the sky. And there is a very nice relationship between the interstellar medium and the star, because what are the properties of interstellar medium impacts, example, star formation, as well as how the stellar mass is being lost also impacts the local interstellar medium. So these two things are affecting each other. And so we want to study these things. Now, studying just interstellar medium is very difficult. As you can imagine, most of you are observing a lot of astrophysical sources, and we are collecting lights basically. And when you have something that is not very bright, such as interstellar medium, it's really difficult to observe them. So that is where this stellar wind bow shock come into play. These are very nice, interesting objects because these are reason of interaction between stellar wind and ISM. Now you can imagine if say in the worst case, you are running somewhere with a very high velocity and you come and interact with a wall, say your velocity will drop down, right? In similar way, you have these massive stars going through these interstellar medium. And a lot of times, these massive stars can be kicked out when they are in a binary where one of the star goes supernova, or they can get kicked out from a cluster. So they can be traveling through these medium in a very high velocity. And when they're stellar wind interacts with the interstellar medium, and if their velocity between those two relative velocity is supersonic, then you can form these structures that is called bow shock. And the name comes from when you have a boat going through water and you have ripples. That is where this name comes from. And one thing to note here is that these beautiful structures are aspherical, so it is not very spherical structure, and this is important slightly later on, but I will be talking more about why it was really important for our study that it is pretty aspherical structure. Now what I want to do first is to give you a broader picture of how different groups from us, other than us, who have used these objects to study different aspects in astrophysics. So first I wanted to look into this one particular paper by Kovalnicki, where they use these bow-shock structures that they observe in our Milky Way and use this to calculate what is the mass loss rate of these massive stars are. And they studied these for 20 different bow shocks, and they found that the mass loss rate that they calculated using observation of these bow shocks actually matches pretty well with the theoretical models they had. And calculating mass loss rate is pretty difficult task to do. So if we can do this observationally for different sources, then it is a really good way, like a good example that we can use these Bow-Shock structures to better understand these massive stars. Another example of the use people have used is to look at what kind of evolutionary phase a star is in. So this is a picture of Betelgeuse. And as you know, we are waiting for Betelgeuse to go supernova. But here you can see it has a nice bow-shock structure around it. And Sajarine Mohammad's team, what they did was they did computational simulations of different kind of for the bow-shock geometry. And they compare it with Betelgeuse bow-shock. And what they found was that this bow-shock structure is very new and it formed very recently. So what it means is that Betelgeuse actually very recently entered the red supergiant phase. Also, this is, I think, would be of interest to all of you. So these are amazing data taken by amateur astronomers, Nicholas and John. So this is a variable star VCVN, and they have been keeping track of how polarization changes with time and magnitude changes with time. And I'm very, very like slightly related, like working with them in a very, very small capacity. But all this amazing data, they took it themselves. And what you see is that these brightness and all are changing with time. And but these are not resolved source. So one of the way that we can explain this variation might be that it has a bow-shock structure around them. And another place where we see a lot of bow-shock structures are near galactic centers. So these are interaction reasons between massive stars, stellar wind, and then you have ISM. And a lot of time where you see high ISM density is where you will see more and more bow-shock-like structures. And the best place for that is obviously galactic center, where the ISM density is very high. And here is an example of different sources that seems to have bow-shock around them. As you can see here, for few, it's kind of clear. For few, maybe not, but they have used, and this is just one example because people have used bow-shock near galactic center to study different properties. But for example here, they use this to study the orientation of the star as well as how the formation happened and in which part or which disk this formation happened. So different groups have utilized different techniques to study this bow-shock and gain more information about the massive star itself, as well as the local ambient medium. Now I would like to switch gear a little bit and talk about our project And first, let's start with what motivated the project. So one of the motivation was that there were a lot of observation of stellar wind bow shock, as you can see here. In this paper, they found around 706 bow shock candidates in Milky Way galaxy. And what it is saying is that a lot of massive stars seems to have these structure around them. And just to remind you, as a group, we were trying to study the impact of massive stars, the type of massive star that turns into supernova. So if a lot of massive stars do have these structures, then understanding this will be important when we are trying to map them with supernova. Also, these are nice, interesting place where we can study about both the stellar wind as well as local ISM medium. And as I said earlier, just observing interstellar medium itself is a difficult task because it is not very bright. But when you have these interactions, you have a lot of emission coming from, so you can get much more photons now from these structures rather than before when it was looking at just the ISM itself. So just studying one structure, we can get some of the properties of both ISM as well as the stellar wind. And now the polarization of light. So this is the technique we use. In a lot of astrophysics, you usually look at the light, study the properties of the light, and gain more information about the source. And a lot of time people do photometry or spectroscopy, but a lot of time we don't do polarimetry, where we are losing a lot of important information. And polarimetry can give you complementary knowledge to what we can gain from, say, just from photometry or spectroscopy. So here, just to give you an example, this is a bow shock near the galactic center, and we can observe polarization coming from it. And this polarization of light contains information about the geometry of these structures, as well as what kind of composition it has. So we can get more information in addition to what we can get from photometry and spectroscopy if we also looked at polarization of light. And then again, the connection between supernova and massive star. And just to give you one example, one type of supernova, which is called interacting supernova, say Betelgeuse goes supernova, which will be really interesting time to observe it. If it goes supernova, then the ejecta from the supernova will interact with these enhanced density around here. And this interaction has a particular line signature in their spectrum, and we call them interacting supernova or type 2n supernova. So this kind of supernova, like we expect, like if a massive star have a bow shock around it, then we do expect there could be these type 2n supernova if these stars explode. So we want to get this more knowledge if we can map that out or not. And then finally, for our project itself, the reason we wanted to do that is because there isn't a lot of computational simulations for these kind of studies where we can get how the polarization signatures looks like depending on different properties. So what we wanted to do was we wanted to create this grid of polarization simulations where you can compare this with your observational data and gain more information about different properties. So now let's talk about polarization, because that is the technique that we use. So I wanted to give you a quick overview of when I say polarization. So as you all know, light is a wave vibrating, electric and magnetic fields. So you can see here, you have blue magnetic fields, in red electric fields. They're always perpendicular to each other. And then they are also perpendicular to the direction of travel. So that is your electromagnetic wave. Now, in a lot of astronomical sources, most of the time, these electric field lines are not aligned in one direction. Now I'm just talking about electric field because magnetic field is doing the same thing, but in a perpendicular direction. So just for easiness, we are just looking at electric field. So you have electric field that is vibrating in all different directions. So that is what we call unpolarized light. And say it is coming from the source, coming towards us, something happens in between, and now you have this electric field aligned in one particular direction. This alignment is called, when we call it, the light is polarized now. So in this case, it is linearly polarized. Now, what could happen that will polarize the light? So example, on Earth, it could be reflection. So you have like this, where you have unpolarized light coming from the sun, getting reflected off, say, lake or some water body, and you have this polarized light. And in order to counteract that, for example, we use polarized sunglasses, where only light polarized in vertical direction can go through. So all these glares from the reflection is not coming in, so we don't see the glare. And what you can do is you can take your sunglasses and try to rotate it at different angle and see how what kind of light you see and how much darker or brighter it gets. Now, in astrophysics, like when we are talking about polarimetry in astronomical sense, there are various techniques you can get polarization. But one of the simplest one that is intuitive and, at least for me, easy to understand is Thomson scattering or electron scattering. So like in GIF here, you have unpolarized light. So sorry, I will start again. Unpolarized light coming in, scattered by electron, and then you get this linearly polarized light. So this is for one photon scattering. Now it could be coming from any direction, so there is no preferred direction, just that if it is a 90-degree scattering, then you get totally linear polarization of light. Now that was for one particular photon, but you have this big region of space where this scattering can happen, and then what happens? So for example, if you have a spherically symmetric scattering region, then each photon after scattering can get polarized in one particular direction. But if it is spherically symmetric, then they all cancel out, and then what we observe is totally unpolarized light. However, if you break the symmetry of this scattering region, and in this example, it is just elongation in the distribution, it can happen in many other ways. But if there is a break in the symmetry, you can see that not everything cancels out, so you get a resultant polarization here. Now, this is just one example. You can imagine if you have some clump in front of this scattering region, that can also produce polarization. Say if we were just looking at part of this region, that can also give polarization. So in some way, you have to break the symmetry in order to get polarization of light. And when we are talking about polarization, we usually talk in terms of Stokes vectors. So there are I, Q, U, and V. So I is the total intensity. Q and U are linear polarization, and V is circular polarization. Just to give you a better representation, what positive Q looks like, what negative Q looks like, and U and V circular. And when we are talking about it, polarization or polarization degree is fractional polarization compared to total intensity. And for rest of my talk, I will be talking about linear polarization and not so much circular polarization. And there is few reasons for that. One is it is hard to observe circular polarization. So there isn't a lot of instruments doing circular polarization observations. But also in case of electron scattering, we don't get any circular polarization. In dust scattering, we can get circular polarization, but at least in our simulation and kind of the work we are doing, we don't get very high level of circular polarization. So we just look at linear polarization. And then this theta is the position angle that gives at what angle this alignment of the electric field is with respect to x-axis. So So that was polarization. And how do we set up the simulations that I have been talking about, like for computational simulation that we want to do? So we started with this simple analytic solution by Wilkin 1996. So here is a sketch representation of how the density looks like in our code. So here, this shape is a bow shock. So from here, we can, using from the paper, we can calculate, we can figure out how the radius changes with different theta value. So theta here, theta is 0 at z direction, and then it increases. And I is the inclination angle or the viewing angle. So we are the observer at what angle we are looking at. And then this R0, or called standoff radius, is basically the distance from the source to the closest point where this interaction is happening. And this equation includes this mass loss rate of the stellar wind, as well as this ISM, local ISM density. So if we can figure out what R0 is, we can also calculate these different properties. This shape is a caveat that it is more for evolved bow shock. So when you saw for things like Betelgeuse, you saw it was much more rounder. So this structure is much more for evolved bow shock. And then the grayscale here represents how density is at different theta values. And the code we use is a numerical simulation. It is based on Monte Carlo radiative transfer code. So I will try to go through like a very simply how this simulation works. So we have a source or a star at the center. You have this scattering medium around. We emit photon from the source, and it goes to the scattering medium. Now in the scattering medium, it can be electrons or dust, and then the interaction happens between the photon and the electron or dust in there. Now this interaction can be that it gets absorbed by the source, but it can also get scattered in some other direction. And we keep track of it. We keep track of all the Stokes vectors as we go along. And in each scattering, we get different Stokes vectors. And so we keep adding up. And at the end, it leaves this scattering medium, and then we observe it. What we do is we bin them from theta 0 all the way to theta 180, and we get how much photon are coming at different angles and what kind of Stokes vectors these different angles have. So this is a very, very simple way to put what we do as a simulations. Now I will go into a few of the results we have using these simulations. So first, these are results when we have electron scattering that is creating polarization, and we are looking at these polarization maps. So what you are looking at is, imagine your eyes can see polarization of light. Then this is how, if you were looking at a cross section of a bow shock, then you will see how polarization of light was distributed in the image. And so there are a lot of things here, but I hope I will make it clear what these results are saying. So first you have central and distributed in these two panels. What it means is that in central case, all the photons are coming from the star itself. In distributed case, we emit all the photons from the bow shock itself. And you can already see that in distributed case, your polarized light is almost concentrated on the edges. And in central, it is much more better coming from all different parts of the bow shock. Another thing is we are looking at two different viewing angles. So 55° is this top one. So we are looking at this direction. And 125 is looking at this direction, just to have two different inclination angle. And you can see that for distributed case, it is hard to say much difference. But for central case, we can see that polarization is much more concentrated at the bottom part, when we are looking at higher inclination angle. And then the next thing we have is different temperatures. And again, for the distributed case, we cannot say much. But for central case, we do see a difference in how polarization maps looks like in different temperatures. So these kind of maps can help us identify where the photon source is, what kind of inclination angle we are looking at, or what kind of temperature it has. Also, a lot of times these sources can be unresolved. In that case, we can create these kind of simulation results where we have polarization or percentage P in y-axis, and then the inclination angle or the viewing angle at x-axis. And again, this is the central and distributed. And these different lines are for different optical depth, or how, in a simple way, how dense the scattering medium is. And as you go up, the density is increasing. So we see that as density increases, we tend to see higher polarization. Another interesting thing we found with this simulation, though, was that at higher optical depth, we start to see the second peak. So in analytical solutions that people have used in the past, they usually say that the peak is at 90 degrees. But if there is a high density, then you can get another peak as well. So in the past, people were using analytical solution to compare their polarization observations, but we do have to be careful doing that, because if it is high density region, then it does deviate from analytical solution. We don't see a lot difference between central and distributed case in this scenario. Now that was all for electron scattering case. And the reason I started with that, and at least for me as well, is that it is much easier to understand and slightly simpler phenomenon. When it comes to dust scattering, it is a lot more, there are a lot more different things that come into play, and I find it a little bit more difficult to understand, but I will try to explain. So a very simple schematic of how dust scattering works. You have this unpolarized light coming in. A scattering can happen in the dust, and then depending on what angle the light gets scattered, if it is 90 degrees scattering, you again see totally polarized light. But if it is at certain angle, like in this case B, then you get partially polarized. And if it is forward thrown, then it is not polarized. So this is a very, very simple way to say it. And the problem with dust is that there are different type of dust, and different type of dust scatters in a very different way. And for our simulation, we picked these 4 different dust types. So KMH and MRN, I won't go into the full name, it is just the people who wrote the papers, but KMH and MRN are dust that is like the ISM dust in our Milky Way galaxy. And it is a smaller size dust compared to this R550 and WW02. And what we wanted to see was, does the size of the dust grain affect how polarization happens? And it has implication, because when you have this interaction between stellar wind and ISM, we wanted to check, does this interaction destroy these dust grains? Say you have ISM like dust, can it get even smaller? Can it get bigger? What happens to the dust when these interaction happen? So that's why we wanted to check how changing the dust size will change polarization. And when we did this simulation, we did it in different wavelengths. And just to note that in electron scattering case, it is a gray scattering. That is, it doesn't depend on what wavelength you are looking at. The scattering is the same. But in dust scattering, it does depend on what wavelength you are looking at. And here are a few different dust properties for all these different dust models that we used. So albedo is how much, what is the probability that it will get scattered versus getting absorbed. So higher albedo means it has higher probability to get scattered. Kappa is opacity of the dust. And then G is the throwing factor of the dust. So what this means is that the G is basically like when you have an interaction, what is the probability that it will get forward thrown scattering happening? And when you have higher forward throwing happening, it means there will be less polarization. And you can see that different dust behave pretty differently. Also that it changes, this property changes with wavelength for these different dust types. So with this dust scattering, we did the same thing initially. We created these polarization maps. And we looked at here, what you're looking at is top and bottom is two different optical depth or density. And then in these two different panels, we have different temperatures, so 750K and 1000K. And then on the top, we have different wavelength band. And then here are different dust types. Now here, one important thing we saw was that at two different temperatures, for H band at least, we can see a difference in polarization map between going from lower temperature to higher temperature. And for other stuff, we don't see a lot of variation between these different models. There is a slight difference, like you can see here for MRN, between two optical depth, we can see a difference in how the polarization map looks like, but just from far, we don't see a very wide difference in these properties. Now, what more important and more interesting result is from these cases, because we can use these to make a better comparison with observations. Now, doing this kind of observation is pretty difficult to have such a good resolution, but doing this kind of observation is much easier. So what you are looking at here is polarization versus wavelengths for different dust types. So these two panels are two different optical depth or density, and the top and bottom are for two different inclination angles. So one, we are looking around this 90, closer to 90 degree, and the other is at 120 degrees. And the Y scale for the bottom one is much bigger than for the top one. And one thing we can see very clearly is that for high optical depth and high inclination angle, we do see much higher polarization degree for all the dust particles. But the way each dust particle behaves is very different from different dust models. And we see similar thing at other viewing angle and optical depth as well. Now, I have been talking about these simulation models. So here is another result from simulation as well. So here what you're looking at is how does the temperature of the dust itself affect polarization. And one thing you can see between, so here's just an example of two very, we picked two dusts that show the most different behavior. And so the top one is for 97 degree inclination angle and the bottom is 120. And one thing we can see is that if we're looking at higher inclination angle, as the temperature increases, we tend to see lower polarization. However, if we are looking at this near 90 degree, as temperature increases, we actually see higher polarization. So this flips depending on what inclination angle we are looking at. And so that is interesting. And also at different wavelengths, it starts to change the behavior depending on how much temperature this dust have. Now, so far, I have talked about simulation, and I know most of you love observations, and you want to know what we could do with these, all this simulation, how we can bring it together with observation. So now let's try to bring this together. So we looked into few different observations that other people have made of different bow shocks and the polarization observations they have done. So here is one of the source near the galactic center, and it's called IRS-8. And they produce these maps of polarization, as you can see here. And that's what I was saying. It's hard to get the resolution that we wanted in our simulation. But still, with the behavior we see in this map, from them, we were able to compare this with our computational simulation, and we constrained the optical depth to be 2, and then constrain inclination angle, at least the best match model from our model that matched this. Their observation was at inclination angle of 50 degrees. Now, what we could do with this? So if you use this equation, so this is just how optical depth depends on your local ISM medium density, standoff radius, opacity, and the C is a constant factor. So we put it in this R0, or the standoff radius, we got it from their observational results. And once we did this, we were able to calculate what the ISM density is. And from our comparison of our model with their observation, we found the ISM number density to be 10 to the 5 per centimeter cube. And this number is very close to the ISM number density that other people have found via different techniques. So we can see that with these models, even though the model is much general, we can compare it with particular Bauschock structure and still get these local ISM number density. Another case we compared it to was this nice polarization maps they had, and more interestingly, they have for K-band and H-band. And you can see these green lines are, the length of the line gives you how much polarization it is, how polarized it is, and then the angle gives you what is the position angle of these maps are. And you can see it is different depending on looking at H-band versus K-band, and how it changes at different parts also changes depending on these 2 different wave bands. And when we compared these with our computational simulation, what we found was that our model showed that the best fit for these models were for a particular temperature, so 750 K, and it needs to be in the lower density side of the thing for the kind of polarization they are seeing. And then the inclination angle has to be in greater than 90 degrees. And as you can see, like the direction of the motion, so we are looking at higher inclination angle, so we constrain around 125 degrees. And we do the similar thing as we did before, and from this we get the ISM number density to be 10 to the 4 centimeter cube per centimeter cube, which matches pretty well with what we have seen before from other observations. We also did this comparison for unresolved cases where there is no polarization map, there is just one observation. And for this, this one thing, we worked with an undergraduate student at the time, Austin Lin, and we observed this one Bauschock candidate. And then we got this green line is the observed polarization value we got. And then we compared it with our different models we have. So here on the top and the bottom, you have central versus distributed cases. And then you have the electron scattering, dust scattering in the V band, and dust scattering in the K band. So we look at different bands. And what we could do is that for electron scattering case, if it was the electron scattering that is the major thing, we cannot say much other than that it has, the density has to be greater than 0.1 optical depth. But most probably it was dust scattering that was causing the polarization. And in that case, we can make few observations. So it has to have pretty high density. And if it is lower density, then the inclination angle will be much higher. And if it is lowered, even higher density, then it can have this different inclination angle. So you can see there are a lot of different things that could happen, right? So we cannot pinpoint one thing. And the same with distributed case, it can have 2 different inclination angle. But if we could observe it in K band, So here are these different possible inclination angle depending on the optical depth. And if we made an observation and had this green line going through somewhere here, we can actually pinpoint now what could be the inclination angle as well as what could be the optical depth of this source, and similar for this. So if we could do multi-wavelength observation of these objects, then we can also constrain inclination angle as well as the density of these structures better, just for the unresolved sources as well. And another comparison we did was with these observations by Buchholz et al., where they did make observation for H, K, and L band, and they have this ratio of how the polarization are at these different wavelengths. And when we compared with our model, what we found was the best fit or the best match with a KMH like dust, which is like ISM, Milky Way ISM like dust. It has to be high optical depth in order to behave this way. And there is no emission coming from the bow shock itself. And we find a very good match between our model and their observations. So here we were able to tell about what kind of dust it requires, the dust size, as well as how much emission should come from the bow shock itself. So these are the things we have been working on. Now moving forward, what are the things we are planning to do in the future? One of the things we would like to do is go from these analytical solution to more realistic solution. Here is an example of density structure from hydrodynamical simulations. And in this case, it will be for one particular bow shock rather than having a generalized case. But we will look into each bow shock structure one by one and do the Monte Carlo simulation through this density structure. Another thing we want to do is observe a lot more bow shock in polarimetry. And one of the things currently that I work with is this telescope, Liverpool telescope in La Palma. And it has a nice polarimeter called MobTop on it. And so one of the observing proposal that we have here is we want to observe bow shock at different parts of the sky so that we can use these techniques to constrain things like ISM density as well as the size of the dust particles. That way we can characterize dust properties at different parts of the sky. And that helps with different things. But for us, just for polarization side of the thing, understanding interstellar polarization is really difficult. So interstellar polarization is basically polarization induced by stuff between us and the source. And we wanted to constrain that. So that is one thing we are doing right now. And we are observing a bunch of bow shock using this instrument in the telescope. And here is just one example of the recent observations we had. And here is your source, here is your calibration star, and then we do see some residual polarization, but this is extremely preliminary results. So we are working on increasing the number of bow shocks that have been observed in polarization. So I would like to conclude by saying that I hope I saw that these structures are really good laboratory and could be used in many different ways to study the properties of ISM as well as the stellar wind. And since these structures are aspherical in structure, they can produce polarization signatures. And these polarization signatures that we observe, along with the models we have, we can constrain various properties ranging from inclination angle to temperature to density of these mediums, to the properties of the ISM density, as well as what happens to the dust type in these regions. So I would like to leave here with acknowledgement to all the people who have helped me quite a lot with these projects. And thank you very much again for listening to me. And I will be very happy to answer any question you have.
Thank you for a fascinating talk and a very good explanation of polarization, which is a tricky topic. I see we're already getting some questions coming in, which is great. And just to remind anyone else, if you'd like to ask a question, then if you could type in the Q&A on Zoom or the comments on YouTube. And just before I get to the first question, I'll just give a plug for our next meeting, which is going to be on Wednesday, the 15th of September at 7 p.m, which is going to be a webinar again on the daylight fireball of the 20th of March of this year. And it will be given by Dr. John Mason, the director of the BAA Meteor section. So I see we've already got 6 questions coming in, which is a good sign everyone's been engaged with your presentation. Matthew?
Would it be better if I stop sharing the screen?
Yeah, feel free. That's then bring the our screens up a bit bigger. So the first question is from Matthew, and he asks, if the bow shock of Betelgeuse is young, how accurately can its age be measured by its geometry to gauge the length of the supergiant phase?
So I think so this is not my work. So, but I think in this case, what they did was they looked at all the properties of say stellar winds and mass loss rate of Betelgeuse that they know from other ways. And they did smooth particle hydrodynamic simulations. So how does the the bow shock looks like at different A's, and they did the comparison between that with how the observation looks like for Betelgeuse. And that's how they calculated that it was pretty young. So it hasn't been stabilized yet. So it must have formed pretty early. So I don't think it is a really exact when it entered this RSG phase. It is more we can see now that it is pretty new. So it's not exact number. It is more tentatively that it entered this phase pretty recently.
Thank you. And next question is from Adam Fairhead, and he asks, if a red giant like Betelgeuse is, say, 250 times the size of the Sun, but is only 10 times more massive, its density will be an order of a millionth that of the Sun. Does that mean Betelgeuse can be partially transparent to a close observer? I can see that might be a slightly tricky one on a different topic. I mean, one thing which I think I've seen from the things we've had, the talks we've had to the variable star section and people who've done work on it, is that the size of a red giant can depend on the wavelength you observe it at, because of the photosphere and probably that kind of effect of, are you looking through the photosphere? Is it transparent at that wavelength, or is it opaque on the opacity?
Yeah, so yeah, exactly. I think it totally depends on what kind of wavelength you are looking at. If I could, I cannot say for sure because I don't work on this, but I would imagine depending on what wavelength we are observing it, right? If we can even observe through the galactic center, depends on what wavelength we are looking at, I would say, but I'm not 100% sure. Sorry about that.
That's okay. I guess not quite your area, but. And then from Darryl Dobbs, he's got a couple of questions, and his first one is, can you tell from your results if the dust grains in the bow shock are spherical?
Yes. So all the models we did, and so I hope you got with the dust, with electron scattering, it is easier to understand. When it comes to dust, it is slightly more difficult. And when we start going into elongated dust grains, it becomes even more difficult because we have to take into account magnetic field, the alignment, and everything. So in our case, we have been using spherical dust. So all of the dust models I showed are for spherical dust. People do look into, so I should have said it, but when we were comparing with different sources near the galactic center, a lot of times we think the dust is not spherical. It must be elongated in some way and aligned due to magnetic field. So that can create different polarization. But keeping track of the elongation, the alignment, and the size of the dust is really difficult. So we went with the simpler model where we can just look at one property at a time. So yeah, but short answer is yes, it is all spherical in the models.
Interesting. And then Daryl's second question is, have you seen bow shocks interacting with other bow shocks?
That's very interesting, fascinating. As far as I know, no. So the interaction actually, like, as far as I know, no. But in terms of interaction, we also see bow shock when we have binary stars, where you have stellar wind coming from both the stars and them interacting with each other. So instead of just one star going through ISM and interaction, instead you have two stars where you have winds coming in and interacting. So these are also another way to form bow shocks. But yeah, that will be very interesting to see, to be fair, but I don't think, like, as far as I know, no. Another thing we have seen for something like Betelgeuse, though, is that you have the bow shock and then you have this like bar-like structure right in front of bow shock. So, but I don't think we have seen this interaction of bow shock with bow shock. That would be interesting.
Keep looking out. So the next question we have is from Michael Poxon, who runs the YSO, the Unstellar Object Group, at the AAVSO, one of our fellow organisations we work closely with. And he's interested in the role of bow shocks in star formation areas. And have you studied these types of bow shock as instigators of iterative star formation processes, possibly in fractal star formation?
So the answer is no, because our focus was more on the evolved massive stars so that we can connect it with supernova. So we didn't do that with young stellar objects, but we did have a chat with someone who was working on young stellar objects who were trying to do these bow shock simulations, but at the time we didn't do it because we were very focused on the supernova side of the things. So yeah, I haven't looked into this side of the things, no.
And then we have a couple of questions from Simon Street. His first is, if you manage to build a circular polarization system, what information what information do you get from this?
Yeah. So like I was talking about, so it is mostly, I think, my understanding is will come from the magnetic field structures. We can get more information about the magnetic field. And once we go into the elongated dust that are aligned by magnetic field, then that's where we start to look into circular polarization. In our models so far, though, like, we don't get high circular polarization, so we cannot like do much. But that is because we are using spherical dust, as well as we are not aligning it with any magnetic field. So with circular polarization, you get a lot more information about magnetic field properties, as well as, like, if you start to get more and more realistic and get elongated dust, then that will play much crucial role.
Thank you. And Simon's second question is about the polarization from magnetic fields. You assume none?
Yeah, that's really so a lot of times, I guess it is a joke that a lot of astrophysicists try to avoid magnetic field because it is very difficult to study. So at least so with magnetic field, now with the work I do with GRB, I do work a lot with polarization due to magnetic fields, but in our simulation of bow shock itself, we don't take into consideration magnetic field. One of the reasons for that was because we are using circular dust grains. It doesn't really matter to us much. But in a more realistic case, we do need magnetic field, because not only with polarization, but also it affects how the bow shock structure will be. So there are people who have been working on magnetohydrodynamic simulations of these structures and how different magnetic field affect how these bow shock structures look like. So it is very, very important thing to look into, but so far we haven't.
Thank you. And the final question comes from John Simpson, and he asks, for stars like Betelgeuse and VCVN, that type of variable stars where there is a pulsation, can you derive any additional information as a result of the way in which the bow shock measurements vary over time of the pulsation.
So yeah, John, it's like the data, part of the data comes from him, so it's amazing. So with pulsation, as far as I can tell with our models, is that what we see is, so in all of our models so far I have shown is, you see just a Bow-Shock structure, right? And the source at the center. So there's nothing between the star and the Bow-Shock, which is not real at all. So what we have seen is that if you have stuff between us, between the Bow-Shock and the source, then it changes polarization. Now with polarization, if it is spherically symmetric or symmetric in some sense, then it starts to depolarize. So say with you have some kind of stuff coming out at different phases, and it is getting, say you have a star, something comes out, it is moving outward, right? After initially, when it is just outside, it can decrease the polarization because of the randomization in the scattering. But once this stuff get all the way to the Bow-Shock, and if it increases the density, then it can increase polarization at the Bow-Shock. So this can happen. And so this is the only way we have seen so far how this polarization can change with time. However, these Bow-Shock are pretty far from the sources a lot of time in a very large scale. So it's hard to say if that's what is happening with star like VCVN, but that is one way where we can see this variation in magnitude or the brightness as well as polarization.
Great, thank you very much. And we have thanks coming in from various attendees as well. Simon, thank you for it, and excellent lecture from David Gwynn, who had to leave partway through, but is going to catch up on YouTube later. And a thanks from Nicholas Steenken, who has a super interesting talk.
Thank you.
Manisha, I'd just like to add my comments. Really good, and thank you for not shying away from using equations as well, because so often people sort of put one token equation in there and leave out the rest. But no, it was really good. Thank you very much indeed.
Thank you, and I hope I was able to connect the equation. Like I try not to use a lot of equation as well, because I think it is not the best way to communicate, but I hope I was able to connect the things.
Really good. Thank you very much indeed.
Thank you.
And thanks everyone for attending, and we hope to see you in a week and a half when we have the next of the Wednesday webinars.
Thank you very much for having me. Bye.
Bye.